Okay, so we're going to be talking about chemical bonds. Chemical bonds are the forces of attraction that hold groups of atoms together and function as a unit. So we've primarily talked about ionic compounds up to this point, but they're also, but they have to do with what's happening with the electrons. So ionic bonds involve transferring of electrons between atoms that have a high difference in electronegativity. So we generally have them as metals and nonmetals bonded together. There's a couple examples I have here: sodium chloride, NaCl, or potassium nitrate, KNO3, are both examples of ionic substances. So we have our cation with our anion. Remember that cation always goes first. So there is an exception to the nonmetals, and that's one specific cation. That is ammonium, NH4+1. That would also have ionic bonds. So they have a strong attraction between the positive and the negative ions, which we then write their formulas in the simplest ratio. These are generally crystalline solids at room temperature. They have a very specific 3D shape, which we're going to talk about later in this unit, and very high melting points. Quite often the melting point for an ionic compound is so high that it makes it very difficult to melt on a traditional hot plate. And they also conduct electricity when they're dissolved or molten. So if they're a solid, they won't conduct electricity. The second type of substance we have is a covalent substance, which shares electrons. So the sharing of electrons, they share because of the smaller difference in electronegativity. One of the common compounds we'll have in covalent substances is carbon, and because carbon often ends up sharing its electrons. An example of a covalent compound would be carbon dioxide, or that's a common example as carbon and oxygen with it. So make sure you cross out metals that should not be here. Covalent substances only involve nonmetals. Their attraction between the nonmetals, and we usually give the true ratio. So for an example of something that you might see would be this substance P4O10. It has specifically 4 phosphoruses and 10 oxygens. Another example would be glucose, C6H12O2. We write the specific quantity. We're going to talk about other ways of writing these a little bit later. But these often have very low melting points. Thinking of carbon dioxide, it's a gas at room temperature. But they can be solids, liquids, or gases. So think of water. Water is a liquid at room temperature, also a covalent substance. The last type that we're going to talk about is a metallic substance. Metallic substances have a positively charged center atom or cation surrounded by a sea of donated electrons. So I'm going to show you a graphic of this a little bit later. But what ends up happening is the electrons are going to move if there's charges. So if you think of electricity, any electrical wire is using metallic bonding. So copper is a very common electrical wire. So every time you have copper, you're going to have the electrons flowing through the wire of the substance. So you can just have one, so written as MgPb, or if it's copper, Cu. There's a range of melting points, usually dependent upon the number of valence electrons. Some have a very high. Tungsten's one of the highest, and they are crystalline solids. So they're often very malleable, meaning they can be hammered into thin sheets, and ductile, meaning it can be drawn into a wire. Both are examples of it. So we're going to take a look below where we're going to identify the types of bonds. So why don't you try this on your own? So remember, ionic compounds are a metal and a nonmetal. Covalent are 2 nonmetals, and then metallic is 1 or more metals. So try it and we'll see what happens. So here we have our covalent and ionic and metallic substances listed. So the only metallic substance is the iron and nickel together. Be careful with the CO, that's carbon and oxygen, not cobalt. So it's very important to write your O's clearly as a capital or a lowercase, depending on what you're trying to communicate. Some of them are kind of a border between ionic and covalent. So silicon is actually a nonmetal for our purposes here, even though it's a metalloid. So there's a specific line, and we'll talk about that more later, that we name it and classify it as covalent. So it's on the nonmetal side. There's also metalloids that are on the metal side, like aluminum. We treat those like metals. So this brings us to our covalent naming. So covalent naming, what we're looking at is we're only going to look at binary compounds which have two nonmetals with them. These compounds involve the use of numerical prefixes. So there's prefixes. This is that makes covalent naming different from ionic. Covalent has prefixes that are used with it. So taking a look at the first one here, we have the number 1. We use the word mono. 2 is di. 3 is tri. 4 is tetra. I'm going to put the A in parentheses, and I'll talk about that in a moment. So 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 nona. And 10 is dec. Now these actually go beyond 10, but for our purposes we only need to know up to 10. So the rule that ends up happening with the vowels in parentheses is we don't write those if the first letter of the element is a vowel. So if you think of oxygen, for example, oxygen, if we have one oxygen, we wouldn't write the O here, or we wouldn't write the A in general, as a general rule. Sometimes there are exceptions to this. If you write the A unnecessarily, it's not a big deal as long as it's not a duplicate letter. So if there is there's a few rules that go along with this. So if there's only one atom of the first element, you don't use a prefix. You only use a prefix for the first element if it's more than one. We name the first element as just a normal element, and then the second element. We change the ending to IDE. We still use prefixes for the first and the second. The first element, we just never use the prefix mono. So let's take a look at a few examples. Okay, so in our first example, we have nitrogen and oxygen. So we have 2, so this is going to become dinitrogen. And then 4 oxygen, so it's going to be tetraoxide. So we actually don't include the A in this because of the O. It's going to be tetroxide. Next up, we have XeF4. So we only have one of the first element, so it's going to be just xenon, and then tetrafluoride. And as always, be careful spelling fluoride. It's UO. So why don't you take a moment and try the remaining 3 on your own. We'll pause the video for a moment. Okay. So we have dinitrogen pentoxide. We have carbon monoxide. You should only have one O there. You don't want duplicates. And then carbon tetrabromide. Whoops, I forgot the M. Bromide. No D. Okay, so then we have to go in the other way. One of the things you'll notice with this naming system, it's much easier than ionic because of the prefixes, but now that you've seen the prefixes, we don't ever use the prefixes with ionic naming. So don't get into the trend of just using prefixes for everything. So the next up we have diarsenic pentoxide. So di for arsenic, which means 2, and pentoxide, which means 5. Phosphorus pentabromide, so that's going to be PBr5. We have the penta meaning 5. Carbon tetraiodide. Now you'll notice there is an A here for this. There are exceptions to this rule. If you miss an exception, I'm not going to take points off for it. but it'd be CI4. Trisilicon, so Si3 tetranitride, so N4. And then tetraphosphorus DEC oxide would be P4O10. Okay. So there's a practice worksheet in your packet. You're going to do your practice, check your answers, and then also there's a vision assignment.